For example, if we have an infinitesimally small dipole, what we often assume, we assume that we have a dipole that looks like this. We orient this one along the z-axis, and we try to determine the A, the E, and the H at some point P at a distance r. And so far, we assume also that we use spherical coordinate system. We use here the angle theta, and we also conclude that we can have here E theta and the H phi. Okay, so far, this is what we have seen for an infinitesimally small dipole in a specific direction denoted here by z. Now, just for sake of to have a look at the way how we can switch from one axis to another, let's assume for a moment that we have a dipole which is pointing along the x-axis. Okay, so let's assume for a moment that this dipole is pointing along the x-axis. This is the y-axis, and this is the z-axis. Now, what has happened is that just the dipole is oriented differently, but the spherical coordinate system is still going to be r theta phi. Okay, so these are two different combinations, but what is common between this dipole being oriented like this and this dipole being oriented like this is that their common part is that they have the same spherical coordinate system. Okay, the r, theta, and the phi. So we want to find here, these were the fields that we obtained using the equations that we just showed. We started last week and we repeated partially today. Now the question is that with this dipole moment, which is pointing along the ax, find these. So let's see how we can determine these. And what we need to denote here is that similarly to this orientation, let's say that this distance r here is now this distance r from the 0, 0 point again, okay? And we can denote here an angle which we can denote this one as psi, and the projection, we are still looking here at the x, y, z. Sorry, x, y, z. This would be the angle theta, this would be the angle phi, okay? And this is the r. This is the upper domain. Now, since we have the dipole looking along the x-axis, we know that there is a specific symmetry along the, so for example, if the wire is looking like this, there is no difference between being in the front of this wire, the back side, to the right side, or to the left side. So, since there is no difference between these, it is good to assume that the first component, at least the A, would be pointing along the x-axis. So that is, so we have one axis psi with respect to the x-axis, and we assume that we have also this, so the projection of this point R is going to be projected on the YZ, and the angle from Y to Z, similar to this equivalent picture, will have an angle using this letter. So here, theta, it will be equivalent to this letter, and whatever we had phi here, we're going to have this other angle. So first of all, let's think it like this, and the first, and let's have a look at the expression for the electric field. You can go over the notes, or you can open the book, and look at this expression of E theta. This E theta, it was composed of several terms, but it included also this angle sine theta, okay? And when we say several terms, we'll have here of course here it will be the current, I0, it is going to be the L, is going to be some 4 pi over r or some other terms we have here. It's going to be also the direction, which is going to be a theta. So you just have a look at the expression, or you look at the book and try to, and you can write this whole expression. Let's come here. Sine theta in this domain, it was this angle. Now, since we have the orientation along x, we want to figure out what is sine psi. Okay, so this is the initial question that we want to clear out. And this one, it can be written as 1 minus cosine square psi square root. Okay, and in here, the angle between the AX, so let's note here, this is AX, okay, and this is AR. Now you can go back to so in spherical coordinate system, we can try to determine what is the dot product between AX and AR. So how can we find this one? We know that AR, it is going to be, so let's think for a moment. Let's go back to these units. This is the AR. So how much projection will have AR over AX? So this is how you can define. And I want to remind you, this is too much, probably to some degree too much repetition, but there is a classical question. What is the projection of vector A onto vector B? Projection. What is this? We always write this one. We say A dot product with B divided the magnitude of B, which is A dot unit vector along the B. So this is how we do it. And when we do it, we should always multiply, or we should determine what is the angle between two vectors. For a moment, this is AR. What is the projection of AR onto the XY plane? The projection of AR onto the XY plane is this vector. It's shorter. By how much? So how much? This is theta again, right? So the projection of AR down to this plane, it is going to be what? What is this component? If we use the angle theta, it's going to be sine theta, right? So depending on this angle theta, that's what the projection of AR is going to be down here. Which means, for example, if theta is equal to 0 degrees, what is the projection of AR onto the XY plane? It is 0, because it's going to, if theta is 0, AR is going to look right here. So then it's going to be sine 0 degrees, this is going to be 0. But if theta is pi over 2, then that means that AR, it's somewhere here and it's pointing along this direction. The projection of AR will be AR again. Or this is going to be a vector with a length 1. Is it clear so far? So the projection of AR onto XY, it is sine theta, and the projection of this one onto the x-axis, we multiply it by cosine phi. Okay, so this was the fundamental quantity that we need to consider. So then, the sine phi is going to be equal to square root of 1 minus ax dot ar all square. And this is equal to the square root 1 minus cosine square phi sine square theta. This is the sine phi. Okay, then if this is the case, now can someone look from the book and tell me the exact expression for this electric field? Am dat și voi te cușna și nimet? Në libri? Or let me look here. We need to find the, I'm going to go back. So from the slides, we can write an expression which is going to be E in the far zone. This is E. This is E5. This is K I0L e to the power minus jkr divided by 4 pi r sine theta. So this would be the electric field along the theta direction in this domain. But now, in this other domain, when we say other domain, when the vector is pointing along the x-axis, this would be equal to j eta k. Now let's not forget k is equal to 2 pi over lambda. I mean, we need it here. Okay. The amplitude of the maximum current, which is I0, the length, which has the length L, this is all the same e to the power minus jkr divided by 4 pi r times sine phi. Now this sine phi that we have here, a second, I want to see the board. So this sine phi that we see here is going to be equal to minus 1 minus cosine square sine square theta. So this is the projection E, this component, as long as we increase this angle. So it's going to be this field around here. If this angle is a little shorter, this is going to be perpendicular to this direction. Yeah. So if this is the projection of the electric field, we need to find the respective. So what did we have here? We had E theta and its conjugate, not conjugate, but its associated vector. It was the H phi, right? Similarly, now we have this component, and this will be associated with H, this Greek letter. And this is going to be equal to, so simply, the magnetic field intensity is going to be equal, so we just cancel out the intrinsic impedance. This is K I0L e to the power minus jkr over 4 pi r times the same square root. So this is the this is going to be the field vectors. Now, once we have this, we can also try to determine. We can try to determine the radiation intensities. The radiation intensities is going to be so this is going to be 1 over 2 E cross product H. So this is a 2. And this 1 over 2, once we multiply with the with the complex conjugate on the H, and by the way, this is these two different angles. Now the complex conjugate of the magnetic field intensity is going to be a negative sign here. That's it. And we're going to have also a positive sign in here. So when we multiply here j with j, it's minus 1. Plus this minus 1 is 1. And also e to the power minus jkr, e to the power plus jkr, they all converge to 1. So then so we are multiplying these, and then what we obtain is that as we are multiplying these two together, this is 1/2. Then we have 1 beta is here, then everything is squared. So if we look at these terms, it's going to be k squared I squared, k squared I 0 squared L squared divided by 4 pi squared times 1/r squared. So this is, we have also, we have to multiply also this term here. So the square root times the square root, this is going to be 1 minus cosine squared sine squared. Okay. So this is the radiated power density. Now the radiation intensity, this U, is going to be equal to the radiated power density times r squared. If we multiply this by r squared, we have that this r squared, it will be gone. So we are going to get the eta k squared I0 squared L squared divided by 4 pi squared 1 minus cosine phi all squared sine theta squared. And by the way, okay, yes, this is like this. So we found the radiation intensity. From the radiation intensity, we can determine the total radiated power. Total radiated power, we can use it here. This is going to be U sine theta d theta d phi. And as we integrate this one, this will take sine theta d theta. So this is all of these terms. These are constants, so they can stay out of the integral. So you can keep here some constant terms, integrating over 1 minus cosine squared sine squared theta sine theta d theta d phi. So in here, this sine theta, this will become sine theta minus sine cube. So this is gone. So then we would have to, well, to conduct or to calculate this integral. Yeah. So this is an example of how, but actually here we did not do much complex, how can I say? We did not do very complex vector calculus. We simply try to use the symmetry between when we had the antenna pointing along the z-axis and the case when we had the antenna pointing along the x-axis. A similar example can be one when the dipole can be pointed along the y-axis. If the antenna is pointing along the y-axis, what would be an essential element which is going to change all the results, but that would be equivalent to this one? It would be probably the antenna pointing along the AY, taking a dot product with AR, and then you may need to figure out here these components. And then the integrals could look slightly different. Okay. Okay, now we can have a look at a different example. let's assume that we have an antenna which is equal to 5, it has some length scale, which is 5 lambda, where lambda is the wavelength that we are using. So this is 5 lambda. The distance where we want to observe, or where we want to do the calculations, so this is going to be equal to 60 lambda. Okay, so this is the length where we want to do the observation, and let's assume that we are in the far region, and in the far region, the R, it's equal to R minus Z cosine theta, okay? And if this is in the far region, the question can be, what is the phase change? So let's try to determine what is the phase change, or let's write it like this. Now, in this case, we have an R, and the expression, without using any approximation, is the following. We have, this is going to be R squared plus, and by the way, let's assume the maximum phase change. Okay, so let's add also this one, the maximum phase change. And the maximum phase change, in fact, we are expecting here something between K times delta R, okay? Because we said that, we mentioned this before, that R would be just the distances between the distance between the center of the antenna to the point where we're doing the observation. We're going to calculate this one with respect to the expansion of the R. And the expansion of the R, we're just assuming the first two terms since we are in the far field regime. Now, let's continue here. We have, this is R squared minus 2R Z prime cosine theta plus Z prime all squared. So this expression, let's remember, this was trying to rewrite again the expression which was x minus x prime squared plus y minus y prime squared plus z minus z prime squared all square root. We ended up in an expression which can be approximated like this, but now since we want to find the maximum phase difference, let's assume for a moment that the angle theta is equal to pi over 2. So if this is pi over 2, then this means that this can converge to 0, and in that case, this is capital R, or that's R1. This can be written as, wait a second, so this is Z1. Z1 squared. So in this case, what we get here, this is going to be 60.052 lambda. Now, this is a distance which is approximated, or at least the general expression of the R, where we have included also the coordinates of the source. Okay. Now we have also the radius R. So this is, let's call this one R1, and we have also this 60 lambda, which is simply equal to R. Now the delta phi, this is going to be equal to 2 pi over lambda, which is a K, times delta R, which is this expression here, and this is equal to 2 pi over lambda times 0.052 lambda. So if we take this out, this would be equal to this is 0.052 times 2, this is going to be equal to 0.104 times pi. So times a factor of 3, this is going to be approximately 0.313, really. So apparently this is the phase difference. The question is 0.313. How does it compare with the threshold which is accepted as an allowed error, as an accepted phase difference in error? So this, we have to check whether this one is smaller than pi over 8 radians or not. Okay. So pi over 8 radians is equal to what? This is 3.14 divided by 8. This is 0.31. What is 8 times 9? What is 8 times 9?
Professor, eu dei 0,392.
Okay, that's enough. So this is approximately 0.13. This is smaller than 0.39. So it looks like at these relevant distances, it is reasonable for us to use this approximation. Okay, to use this approximation because we are less than the accepted phase difference, which, as we said before, this would be the distance between. This was 2 pi. This was pi over 2, pi over 4, pi over 8. So we are something less than this. Okay.